So look, I'm curious, by a quick show of hands, how many of you have taken a calculus class at some point in your life? All right. By another show of hands, how many of you found that class to be riveting? So math class, and calculus class in particular, tends to get kind of a bad rap, much to the dismay of mathematicians like myself, because calculus is a subject that happens to contain some extremely powerful and imaginative ideas. And if you don't mind, I'd like to share a couple of them with you right now. Imagine an object in motion. It could be a car driving down the highway, or a drop of rain falling to earth. It feels obvious to most of us, I think, that at any given moment in time, that object is traveling with a certain speed. But what can we possibly mean by such a claim? The Greek philosopher Zeno of Elea, who lived 2.5 millennia ago, was so perplexed by motion that he cast it as paradoxical. How is it, asked Zeno, that an object's motion is possible in the first place when, at any given instant, if we freeze time, the object doesn't seem to be moving at all? That question might sound a little silly at first listen, but the more you think about it, the more you'll realize just how difficult it is to answer. One brilliant way of thinking about this problem, 2,000 years in the making, came to fruition with the work of Isaac Newton in England and Gottfried Leibniz in Germany, who reasoned about this problem in the following way. So, look, as you watch that object move through space, you can imagine that it's traveling along a number line, occupying different numerical positions at different points in time. This, in turn, allows you to plot the position of the object as a function of time, like this. Now, suppose you want to understand something about the object's motion at just a single instant, like this point in time shown in the picture. Here's the idea. Take a second point on the position curve, then get out your ruler, measure the change in position between those 2 points, that's this vertical distance right here, and divide it by the corresponding change in time. That's this horizontal distance here. Now take that second point on the position curve, move it a bit closer to the first, and measure again. And again, and again. The remarkable fact is that it's possible to describe what happens at the very limit of this process, as our window of time shrinks down to just a single moment. This, in turn, allows us to give a precise mathematical description of the object's motion at just one point in time. This idea, which applies not just to moving objects, but to any quantity that exists in a state of change, gave us a conceptual revolution, allowing us to think about and solve problems not just in math, but in every branch of science, in engineering, and in economics in a totally new way. Here's another problem that fascinated the ancient Greeks. Suppose you behold out there in space a certain region whose area you would like to know. Suppose, for example, that you want to find the area of this swimming pool. Of course, if the pool had the shape of a rectangle or the shape of a circle, then finding the area would be straightforward, but what if it has a weird shape like this? Well, this time, the insight of Newton and Leibniz is perhaps even more remarkable. Take a look at the upper boundary of that pool, and just imagine that it describes the speed of an object in motion, just like our object from before, as it travels in between 2 times A and B. And it turns out that the area underneath the curve, which Leibniz denoted like this, is nothing other than the distance that the object travels, its position at time B minus its position at time A. In one fell swoop, the task of computing a complicated area is reduced to taking a simple difference of 2 numbers. This insight, which likewise has myriad applications, is known as the fundamental theorem of calculus, and it counts in my book as a really beautiful idea. So, like many others, I teach calculus to college freshmen every year. In fact, in the US alone, over 1 million high school and college students study calculus annually. It's worth asking, I think, how do they experience this grand subject? Well, I'm afraid that a lot of them look a bit like this. Or maybe like this. Turns out that to students, calculus is too often seen as dry or impenetrable or terrifying or just some hurdle that they have to leap over in order to get to what they really want to study. And math teachers everywhere must endure the perennial question, when am I ever going to have to use this stuff? Which to be honest, always makes me want to say, isn't that a little bit like going up to Van Gogh and saying, listen, Vincent, Starry Night is nice, but these paintings of yours good for anything? Like, do they have any practical applications? Don't you see how the work justifies itself and that contemplating it enriches your life? I claim that math, like painting, can be an intrinsically meaningful activity. But of course, the story doesn't end there. Because calculus actually is useful. Indeed, it is the gateway to the STEM fields. It's a subject whose central ideas anyone hoping to pursue a career in science, technology, engineering, math, even economics and finance needs to understand. And yet, according to a recent study conducted by the Mathematical Association of America, at least 1 in 5 students don't succeed in calculus at the college level. At least 1 in 5 students get a D or an F or drop out of the course entirely. So what's going on? Well, look, I don't pretend that this statistic can be boiled down to a single cause, but I do think that a huge part of the problem is not calculus itself, but the way in which calculus is typically taught. And if you think about it, calculus education has barely changed in over 100 years. Let me describe for you in a nutshell what I'm going to call the standard model of calculus education. It may as well be called the standard model of math education, the way in which the subject is typically taught. It goes something like this. Step 1, buy a thick, heavy, expensive calculus textbook, priced somewhere at $200, and in which the entirety of the subject is laid out in excruciating detail, with key theorems and results neatly boxed on every page like they'd been handed to us from the gods rather than produced through human imagination and struggle. Step 2, attend lectures where you are never called to action or made to consider an idea on your own, but rather where you're treated as a totally passive recipient of knowledge, sitting quietly at a desk while a professor at the front of the room lectures out of that expensive book. Step 3, solve homework problems that emphasize formulas and rule following, but that tend to obscure the very ideas that motivate the entire subject in the first place. And finally, more of the same, except this time in the form of nerve-wracking, high-stakes exams that will determine whether you pass or fail. Several years ago, our math department was teaching calculus according to the standard model. And several years ago, we faced a crisis. Our DFW rate, that's the percentage of students who are getting a D or an F or withdrawing from class, was an unacceptable 35%. And, unsurprisingly, student satisfaction, as measured by course surveys, was extremely low. In the face of this crisis, my colleagues and I realized that it wouldn't do to make superficial changes to our curriculum. We needed to fundamentally change the way we teach. Now, having been along for much of this journey, I can tell you that the kind of pedagogical change we had in mind is not easy. It took years of experimentation and effort. It's something that requires close collaboration among our faculty, and that also crucially required communication with students, who often weren't used to thinking of math class as anything other than what you get with the standard model. I can also tell you that this kind of change is, in my opinion, not only worth it, but essential. So let me tell you what some of the things we did are to change the way we teach calculus. For starters, we decided to get rid of that expensive textbook. My colleagues and I realized that we could simply write up our lecture notes, polish them, and make them available to students online for free. We retooled our lectures so that they contain an active component, so that students would be asked to solve problems in class, and not only that, but discuss them, both among themselves and with the instructor. We redesigned almost all of our course materials so that they place an explicit focus on concepts, and we made it clear to students that not only would we be asking them to focus and be tested on routine problem-solving skills, we would also be asking them to understand the big ideas of the subject. And finally, being an institute of technology, and recognizing that today's students have digital literacies that previous generations simply didn't have, we got rid of written homework assignments as well. We designed a calculus learning platform that allows students to solve problems in a totally free-form manner. Using the software, students can enter every step of the solution in whatever way they like, and if they happen to be on the right track, the software is capable of providing instant positive feedback. On the other hand, if students make a mistake in the course of problem solving, then the software can recognize that mistake in real time and, in many cases, offer detailed feedback to help the student understand exactly where they went wrong and improve. The software can grade homework assignments automatically, and in case a student has the wrong final answer but has strong supporting work, we'll automatically assign them partial credit. And since this software is recording and analyzing all of the mathematics that students enter, it's able to provide the instructor with detailed analytics that help them understand both where the class as a whole and where individual students are struggling and succeeding. Since implementing these changes, we've seen our DFW rate drop from 35% all the way down to 10%. We've seen an increase in student satisfaction and in freshman retention rates. And crucially, by rethinking the way that we can teach calculus, we've generated ideas for teaching other subjects differently, both in the math department and beyond. If you're an instructor teaching a subject in accordance with some standard model that's outdated and that isn't engaging your students, then I encourage you to think about how you can teach differently as well. You can make a change that occurs at the level of your institution or a change that occurs at the level of your classroom, like making your lectures more active. Whatever it is, if it helps make the subject come to life in the minds of your student, then in my opinion, it's worth it and much needed. When students first see the fundamental theorem of calculus, they sometimes see this, and only this, a formula. You know, it's like reading Shakespeare but only paying attention to the spelling and the grammar, failing to understand that the words on the page actually mean something. And it's human nature. It's the path of least resistance. The student says, look, professor, just give me the rules for succeeding in your class and I'll follow them. But that's not how learning works. The great irony, as I see it, is that instructors can fall into the exact same trap, teaching their subjects according to the same old methods and the same old formula year after year. The instructor says, look, just give me the rules for teaching this class and I'll follow them, but that's not how education works. I believe that just as students must beware of formulas, so too must educators. Thank you.